Welcome to the course Risk Management and Insurance. In this first lecture, we review how interest rates are calculated. Mathematical series are important in interest calculus. Distinguish between a progression and a mathematical series. A progression is simply a sequence of numbers, A1, A2, A3. In a mathematical series, those numbers are added up. So a mathematical series is actually an addition of numbers. There are many types of series with different properties. In financial mathematics, in particular, arithmetic series and geometric series are important. In an arithmetic series, the difference between two consecutive terms is constant. So you begin with an initial number, A1. Then to this number, you can add a constant t. And then you add the constant t again. And you add the constant t again, and so on. D is called the common difference. So a mathematical series actually increases in a stepwise fashion, the step always being D. Now expression 1 gives you the nth term of the series. And it's quite obvious how this works. You see here, if the fourth terms of the series, 1, 2, 3, 4, you have actually here the number 3. So it's n minus 1. So you have the initial term A1, and then you add 3 times D. Now the sum of the first n terms is given by equation 2. So the sum is an initial item, A1. It's a final item of the series, the final number. And then you multiply by n divided by 2. This formula of the sum of the first n terms of an arithmetic series is well known and even discussed actually in high schools. Now, geometric series are different from the arithmetic ones. They are based on multiplication. So you have the first term, A1. Then you multiply by the so-called common ratio Q. You multiply again by Q. You multiply again by Q, and so on. Now here, the nth term is given by equation 3. Again, up here in the power, you have n minus 1 and not n. So the fourth term, the power is 3. Now the sum of the first n terms is given by this equation here, by equation 4. And we will show in the tutorial how actually this formula can be derived. Now, mathematical series may or may not converge. That's also apply to a geometric series. So, if you have a geometric series, you multiply the q, let's say the q is 2. Then you have A1 times 2, A1 times 4, A1 times 8, and so on. You add bigger and bigger terms. And so obviously this series cannot converge to a finite term. It will go to infinity. But if q is less than 1, then the series will actually converge. If you have A1, and then A1 times 0.9, for example, A1 times 0.9 square, A1 times 0.9 to the third power, you will add smaller and smaller items. And even if you have an infinite number of items, the series actually is converging. So we have here a very useful formula. An infinite geometric series converges if and only if Q absolute terms is less than 1. Again, we will show in the tutorial how equation 5 can be derived. Now let's make an example. Let's assume A1 is 100, and then we always multiply by Q. So that's A1 times Q, A1 times Q squared. We take Q as being 0.8. And we add all those items up. So Q is less than 1 in absolute terms. And but so the series actually has a finite sum. The series converges to the finite sum, which is given by this equation here. If we calculate the first 10 terms of the series, we can take the earlier equation. It was equation 4. We can take that one. You plug in, you get 446. Now, if you want to know the sum of all infinite items of the series, then you take this sum formula to infinity, and you will get 500. What this shows is actually that the series, if you add more and more items, it will approach, the sum will approach 500 from below. This always, students sometimes are a bit astonished by this. You see, we have here an infinite number of items, but still the sum is actually finite. The series is set to converge. Now, let's go to interest compounding or interest calculations. So-called simple interest is actually based on an arithmetic progression. Our invested capital V0 increases in a stepwise fashion. And the step is just calculated as the initial capital times the interest rate. So if our initial capital is maybe $100, the interest rate is 5%, then D will be $5 per year. And after T years, okay, we just get those $5 T times. So you begin with the initial capital, then you get $5, another $5, another $5. You get it just T times after T years. It's increasing in a stepwise fashion. And we obviously can factor out the initial capital V0. Now, one thing may surprise you here a bit. Why do we take T here? And why do we don't take T minus 1? But that's the case because actually here our series starts at time 0. And in the early formula, we began the series at time 1. You see this arithmetic series here begins at time 1. And so actually the fourth term we have here n minus 1 gives me 3. Now, if you begin the series at time 0, if you call the first term of the series A0, then actually you would have here a 4. And so you have actually here n. So we can apply here in equation 6, we can apply the early formula from the arithmetic series. An arithmetic series actually follows an arithmetic progression. You have a sequence of numbers, and this sequence of numbers shows you how your invested capital increases actually here in a stepwise fashion. Now, compound interest. Compound interest is based on a geometric progression. It's based on multiplication. You have your initial capital, V0, and then you multiply with the interest rate. So maybe you begin with $100, and then you multiply with 1.05. So after 1 year, you have $105. And then you multiply again, so it's $105 with 1.05. And after 2 years, you get a little bit more than $110. So you see, you get interest on interest. And then you multiply again and again and again. So with compound interest, you get interest on interest. Earlier, with simple interest, we did not get interest on interest. Again, you can compare this with the earlier equation, and you will see up here we have now t. That's because we begin again at time 0. We do not have t minus 1 for the. Yeah. Okay, this formula here, we can expand a little bit. We can make it more general. Let's compound not annually. Let's compound actually more than once per year. So actually we could compound semi-annually. Then you divide the interest rate by 2, but then naturally you get the interest twice as much. Okay, twice as many times. Or you could actually get the interest rate each month. So you divide by 12, you get a small interest rate each month, but then actually you have a lot of months. So that's a more general formula. Here, just simply, okay, you work with annual compounding. Here you can work with semi-annual or monthly accounting or even daily accounting. Let's make an example. So we have an invested capital of $1,000. The interest rate is 10%. I always express the interest rate as a decimal fraction. And after 5 years, we will have, our investment will have a value of $1,611 with annual compounding. If you do semi-annual compounding, then each half year you get 5%. But then you have twice as many half years. So also multiply by 2 up here. You get the interest payments on 10 times in those 5 years. And in the end, you will have $1,629. Now, if the interest payment is done daily, then each day you get a very small amount of interest. But you have a lot of days. You see, we have about 1,825 days here. So we have a very big power here. And your capital will increase, your investment will increase to a value of $1,649. So what you see here is daily compounding accrues faster. So it's, if you think of the point of view of the investor, it's better to have 5% semi-annually than to have 10% annually. You see, we have here $18 more in the end. And it's even better to get the interest payment daily. Then you get an additional $20. Now, we said it before, the annual compounding formula here is just simply a special case with n is equal 1. This is very well-known formula. So that's more general here. Okay, we do here the compounding more than once per year. Today, bank accounts are often use daily interest on compounding. Just read the fine print of your banking account. This was different when I studied in the 1960s and 70s. There were no personal computers, there were also no pocket calculators, and then actually we didn't do daily compounding because, okay, how do you take a 1,600 power? That's not easy. Okay, you don't want to multiply 1,800 times. What you actually did, you converted everything to logarithm, then you multiplied by 1,825, and then you converted back into non-logarithmic figures. So there was a work involved here. And so actually 50 years ago, interest compounding was really based on annual compounding. Nowadays in bank accounts, it's very common to see daily compounding. What you also see here in a credit contract, it's very important that you stipulate the interest compounding. For the borrower, it matters. 10% annual compounding is less than 5% daily compounding. Here, the borrower pays more, okay, than here. Up here with annual compounding, the investor earns less. So a credit contract should actually stipulate, okay, so compounding period of interest rate. Is it annual compounding? Is it semi-annual, monthly, daily, or whatever? Now, if it's not written in a credit contract, I guess in a court case, probably the court would say the default is annual compounding, because that's people are most used to that. But you cannot be sure, so you better stipulate it in the contracts in financial markets. Yeah, we can now ask a question: if it's possible to do annual compounding, daily compounding, we could actually compound even faster. Okay, let's compound every hour. Let's compound even faster. Let's compound every second. So actually, in that case, m goes to infinity in the formula. Remember the formula here. So m, just getting bigger. Okay, with seconds, and actually you have millions of seconds. You divide by those m, or you could actually go even with half seconds. So then it becomes continuous. And the interest rate, your capital will increase at a continuous rate. Now to show what happens, okay, you have to rearrange the formula a bit here, the equation a bit. So this step, I do actually two steps here. I introduce this outer bracket. And you have it here too. Now, if you don't like this outer bracket, then just dissolve it and multiply the powers. You know how that's done, the power of a power, you multiply the powers. And so the r will cancel out, you just get mt, and that's what you have here, mt. The second step I did with this equality sign, okay, r divided by m, I'm writing down as 1 divided by m divided by r. You know this from basic mathematics. You divide by a fraction by multiplying with its inverse. So here 1 should be multiplied with the inverse of m divided by r. So actually you get r divided by m. Now, so you should actually think here, maybe if you have problems with this step, you should think from the right to the left. Okay, dissolve the bracket, multiply the powers, you get mt, and then actually here you divide by the fraction m divided by r. So actually you should multiply with the inverse of it. So that's r divided by m. Now, when a mathematical expression looks a little bit unwieldy, then sometimes you just substitute terms. Substituting terms means you rename them. So instead of m divided by r, I'm writing now s. I just rename m divided the fraction m divided by r. I just name it now s. So we have the s down here, and we have it up here in the power. Here. Now note that when m goes to infinity, also s will go to infinity. So m goes to infinity implies that s goes to infinity. And then the question is, okay, what happens to this expression here when s goes to infinity? Okay, before I had those classes online, I naturally could ask students what will happen. Most students gave the right answer, but some argued that actually the expression here will go to 1. And the argument they made, okay, 1 divided by something very large, 1 divided by something that approaches infinity, because this approaches 0. And then 1 to the 1 to the infinite power, okay, this is still 1. Okay, so students actually claimed, okay, this must be 1. But it's not true. Okay, this expression here, when s goes to infinity, okay, approaches actually the exponential number 2.718. So we can actually plug this into on the equation on the earlier page. You see this part inside here. This goes to E. And then we still have this power here. So this inside goes to E, and then we have still the power. So what we get here is just a very well-known formula of continuous growth that you know actually from science, from the natural sciences. So when a capital or an investment grows continuously every second or faster, yeah, okay, just a standard formula from natural science. It's a standard growth formula from natural science applies. In continental Europe, E is usually called the Euler number, okay, after Leonhard Euler, who lived in Basel, okay, Switzerland. But it's also called the E number, or it's called the exponential number. Now, notation, when things grow continuously every second and faster, when things grow continuously, you should actually use here those big brackets here as with functions. So that's a capital at time 0, that's a capital at time t. Now, when things grow in discrete time, when you apply discrete time, then actually you will take a subscript, or you should take a subscript. So you see here, I always took subscripts here because we have here annual compounding. Here we do also discrete, it's still discrete, maybe monthly compounding. So we are using subscript. That's just notation. People do it that way. All textbooks do it that way. Okay, so there's nothing really deep in that. Now let's make an example. So world population today is roughly 7 billion people, and the annual growth rate is 1.1%. Now that's about correct. The population in African countries still grows maybe at the rates of 3–4%. Also Afghanistan, I think is up 4%. But then in the developed countries, Europe, the population growth is actually much less. Actually, in some countries, populations may even fall, like Italy or Russia. Now, on average, it amounts to about 1.1% population growth in the world per year. So what will be the population in 50 years? I do now here continuous compounding. You see the population grows continuously every second. So let's, the formula is a continuous growth formula from the natural science. I use here the big brackets like the function notation. And you see here, okay, the growth rate is 1.1%, always using, okay, the decimal fractions over 50 years. And what we get is 12.1 billion people. Now, compare this actually with annual compounding. Let's assume, let's take the formula from annual compounding. Here, 1 plus the interest rate, 1 plus r to the 50th power. It's a very common formula. You get 12.09 billion people. It's very close. So continuous compounding is actually a good approximation for annual compounding. But today, finance books, more advanced finance books, no longer use annual compounding. They actually use continuous compounding, and that's particularly because the mathematics in the end is simpler. You see, it's very easy to take a derivative from the Euler number. And you take a lot of derivatives in finance. So you can apply calculus easy. It's more cumbersome if you want to do it with annual compounding. Okay, this finishes today's lecture. So what we have done today, we have looked at progressions and series, and we have discussed simple interest, which is stepwise. Your capital increases in a stepwise fashion. You don't get interest on interest. Then you have compound interest. With compound interest, actually you get interest on interest, and you get actually the exponential growth formula that you know from science classes. And it's quite a neat way, okay, to derive actually the exponential growth formula. You can start here with this example. You go, okay, through this equation. So if s goes to infinity, this goes to e, and you have actually the exponential growth formula. Okay, that's for today. Thank you.